now, so just be aware we're on. Um, so chapter 10 is rotation and torque. And really what's going on is that this whole semester, we've talked about what's called linear or translational movement, meaning we've talked about objects that traveled in straight lines. They might travel in the X direction or the Y direction or the Z direction, or they travel at some, you know, along some path in a straight line. But we now need to worry about rotation, and specifically what rotation, um, how energy and work and forces and all those things cause an object to rotate, or the energy that an object has when it rotates. So if we imagine that we have a block, we've talked a lot about blocks sliding. You know that that block is made up of a lot of little tiny bits of mass all stuck together. But we assume that when that block moves, all of that mass moves with the same velocity. So if we do what's called in calculus an infinitesimal, so if we say that block's made up of a whole bunch of, dm or infinitesimal bits of mass, um, it's made up of a whole bunch of these. They all move. Each little dm moves with the same velocity. And therefore, the kinetic energy is just the kinetic energy of all those little bits all added together. We just write it as big mv squared over 2, but in a sense, we don't have to worry too much because we know they all travel with the same velocity. Now, imagine something rotating, and I don't know if you all have record players or have ever thought about like a merry-go-round or anything that goes around. But when you have a disk of matter, and let's say it's rotating through its center, so it's rotating in that direction. A point on the outside has to go around, and that distance around in one rotation is 2 pi r. Well, that r for an object all the way out here is much longer than for, say, an object at half the distance. And if it's a solid piece, a solid object, as it rotates, points inside closer to the center actually go slower. They have less distance to travel in the same amount of time. That's very different from a block sliding in one direction, because the block, all the little masses all have the same velocity. Now, on a rotating object, all the little pieces of mass that make up that object can have different velocities. And so we need to figure out how to determine the kinetic energy when all these little masses have their own kinetic energy. And it's very different depending on how far away. We need to figure out how to make something rotate and what it means to rotate. Because unlike a block, we can imagine that we push a block with a force and we get an acceleration times mass. But if we push on this disk, is it going to be the same acceleration, same velocity if we push on the outer edge or inside? Or we just need to come up with a mathematical way to describe rotation, and it's going to be very different than what we've done so far. All the bones of it will be the same. We're still going to have acceleration and velocity and displacements, but things are going to have different names. And instead of using dot products, we're going to have to use cross products, and we'll talk about that. But basically what it is that each mass now can have an independent velocity. And we have to consider a whole bunch of them. So we have to consider solid objects. We can't consider these things to be point masses. We could, but we can't. Actually, we could, but we're not going to. In a weird way, we could. So Our job is going to be to define rotation with variables that are analogs to X and analogs to V and analogs to A. And it turns out that, we'll see in a moment, but I'll tell you now, that the kind of most sensible thing to use for displacement of a rotation is the change of angle. So we're going to use theta. We're going to use theta as our X, and we're going to determine how theta changes with time to get an angular velocity. And we're going to determine how that angular velocity could change with time to get angular acceleration. And we'll talk about all that stuff. In doing so, we're going to have a new version of Newton's second law. And so that should be obvious in a small way, or maybe it's not obvious yet. But if we think about it, that this is in meters and this is in radians, and radians aren't units, they're just a number. So we're going to have to figure out how to change force to give us something that has actual units of force in order to get rotation. We'll get to that too. Another problem is, and this goes back to day one pretty much, we talked about when force equals mass times acceleration, we talked about how mass is actually a measure of how resistant an object is to being accelerated. That's what it is. We tend to think of it as weight, which is wrong, because weight is the force of gravity. We tend to think of it as the amount of stuff, but what it really is how much a system or an object resists change, how much inertia it has. It's a measure of the inertia. And so we need to come up with a new quantity of inertia for an object that rotates. It may be much harder to rotate an object if it's long and skinny versus round and symmetrical. And we'll totally see that. But we're going to have to come up with a new quantity of inertia, a new mass, if you will, that affects how we rotate an object, how easy it is to rotate an object, how fast we can rotate an object. And then we're going to rederive energy and work with some rotation ends. We're not really going to rederive it. We're going to add rotation in when we have a system that not only slides to the left or right or falls with gravity, but also rotates during that action. So that's the trajectory we're on. I know it seems like a lot. Hopefully it's not, but essentially what we're doing is we're describing rotation. And we haven't talked about rotation before except for uniform circular motion. And so now we need to talk about rotation. And then if we have a rotation in our system, we need to deal with it. Okay. That all being said, the first thing, as I said, we are going to use the change of angle to be our displacement. So what I mean by that is, imagine that at some point, and you can say this is X and Y, you could say this is whatever, but at some point we have an object. I'm sorry, I need to move this over so that I can draw a little bit better. Let's say we have an object that lays at some distance r from a point, and that object moves in a circular path that can be described by a change of angle. So let's say as it moves, it changes by 1 degree or something. This distance is the trajectory of our mass. So this is our mass. This is the change of s. I used to know what s meant. I believe it's Greek, but that change of distance is actually what we're measuring with rotation. However, we care about theta. We don't care about s. Unless for some reason we need to change things back to Cartesian and linear or translational. In general, we can do everything with rotation with angles. And we will be doing everything with angles. So the other thing I should say in the class is we're always going to 99.9% of the time assume that R is not changing. So things are rotating at a constant R. Why? Imagine you have a basketball and you spin it. All the little masses are spinning around wherever the axis of rotation is, but they keep constant R. Unlike uniform circular motion, we're going to assume that the velocity can change. Okay, so we're not going to have uniform velocity, but we are going to have constant radius, and therefore we can get this nice arc length equation. To prove this to you by a picture, imagine you have a very small triangle, so small that essentially dr, ds, d theta, r is actually a constant, so I shouldn't say dr. We know from trigonometry, tan theta is s over r, is y over x. If you use the small angle formula, you can write that as theta is equal to s over r. From this, we get this relationship. This is actually going to come up again next chapter, but this is actually a condition called rolling without slipping. And what that means is if s changes by some small amount, theta changes by an equal small amount, and r is constant. Okay. That tells us this is how far it travels around its circular path. This is the change of angle. This is the radius. Now that we have that, we can do a couple things. We can actually take a time derivative of both sides, and we're going to do that next. Remember that the time derivative means that if we had something like theta is equal to 4t, taking the time derivative would give us 4 or whatever. So if we were given s as a function of t, or we were given theta as a function of t, we could find something. In general, we're not going to be given that. I know you can all do simple derivatives, but this is what I care about. When I take that time derivative, this thing right here, remember, about some axis, we have a mass, and it's essentially traveling in a straight line. So we call this s, but you can think of this as like x. How s or x changes with time is velocity. It's linear velocity. So this thing has some linear velocity, vt, or translational velocity, velocity in the y direction or the x direction or the z direction, whatever direction that happens to be. But it's also traveling around. And as it travels around, the angle is changing with time. And how fast the angle is changing with time is d theta dt. We call d theta dt omega, this w. Omega has units of rads per second. I cannot stress this enough. Rads are numbers, but they are not units. So omega, unlike translational velocity of meters per second, omega is just rads per second. It's just 1 over seconds. That shows up in the period. If I wanted to know how long it took to go around in uniform circular motion, the period is in seconds, and that would be 2 pi over omega. I can show you why that is in a second, but so we have this says 2 pi rads divided by the radians per second, and assuming that it went around once, it would go through 2 pi rad and rad per second. So this is the time it would take to go around once if we know omega. Omega is d theta dt. But when I plug these things in, I get this really nice relationship. The translational v, the v along here, is equal to r times the angular velocity omega. I will sometimes put a little dot above this. I do that to remind myself that that is not work. That is not some other weird variable. That is straight up angular velocity. It's how fast the angle is changing. Now, we can also divide this up. Or I mean, take the time derivative of this. And what happens? Well, you should know what happens because we've done this before. If I take the time derivative of the velocity as it travels upward, I get a translational. I get the translational acceleration. That's not the acceleration that we learned from ARAD that pointed inward. It's how fast the speed along the path is changing. This quantity here is the angular velocity time derivative, and that is something called alpha. Alpha is how fast the angle is changing with time, twice. So alpha has units of rad per second squared. Sorry, had to answer a text. So alpha is the acceleration, omega is the velocity, and theta is the displacement. Much like we had x, b, and a, we now have theta, omega, and alpha. That is what we're going to use whenever we have rotations. But for alpha and omega, we have a simple relationship between angular acceleration and translational acceleration, and angular velocity and translational velocity. We will use those later on. We'll come back to that later on again and again. So we can relate the variables of rotation to our normal linear or translational variables should we need them, and we will need them. But for now, just understand that we have a new set of variables. We're in a new space, and that space is the rotation space. I'm not going to spend a super long time on this. I think you all understand this. If we want the average angular velocity, it's the change in angle over the change of time. If we want the average angular acceleration, it's the change of angular velocity over the change of time. If we want the instantaneous, we take the time derivative of theta to get the angular velocity. If we want the instantaneous, we take the time derivative of the angular velocity. That's exactly what we did before. And I will tell you that you almost never use the average value unless you're doing something weird. You almost always just want to find at a specific t, either the instantaneous velocity or the instantaneous acceleration. And what I mean by that is if theta were given by 4t squared minus t to the half, at time t is equal to 1, omega instantaneous is d theta dt, so that would be 8t minus 1/2 or 7.5 rad per second. And alpha at that same time would be d theta dt, which would be 8 rad per second squared. Okay, you could find, and I'm not going to because it's a waste of our time, we could find an average by plugging in for, say, t is equal to 1 and t is equal to 2, plugging in numbers and finding them and then finding their average. I don't want to do that today. We have much more important things to talk about. This one is going to get somebody in the class. Somebody in the class is going to mess this part up. So I need you to understand something really, really important. Since you've been doing calculus or even algebra, you've used a coordinate system where y and x look like this. Positive y is up, x is to the right, the origin's at the center. When you start doing three-dimensional, you usually draw x coming out of the page, y going to the right, and these are the positives, and z going up and down, okay? So this is positive z. So we're in three-dimensional graphing coordinates. This is a right-hand coordinate system where if I start the angle at the x axis and move around counterclockwise, my angle increases, okay? And if I go the opposite way, my angle decreases. Now, we're going to assume in this class that anything that's rotating or anything that's moving is in an XY plane. And what we need to do is figure out what direction the rotation is in. And this is where things get weird, okay? So what I'm saying by right-hand rule is if Z is up positive, it has to go X and then Y, so that when you go from X to Y, that direction is positive. If I'm rotating through an angle in that direction, take your right hand, put your thumb in the direction of Z and curl your fingers of your right hand. That is counterclockwise. That is the direction of rotation that if an object's rotating that way, we're assuming that Z is positive upward. And if you put your thumb down and you rotate the other way, clockwise, that is negative rotation. So technically, whenever we talk about a rotation, we're going to be talking about that rotation in the z-axis or in the negative z-axis. And we need to understand that those vectors are drawn as vectors. We did it in the vector lab, but they're not actually vectors. If I have something rotating, like I have a plate spinning around the axis, okay? And it's spinning around the origin in this direction. So I know it's positive. I say that it's rotating around the positive z-axis, and therefore I say the rotation vector points up along the positive z-axis. Or if it's rotating the other direction, so now it's rotating clockwise, I say that the rotation vector points in the negative z-hat direction. But they're not really vectors. They're not vectors because if you go on in calculus and on into things like linear algebra and vector analysis, you're going to find that rotation vectors don't always behave the way they're supposed to on reflection and other things. They are a pseudo vector. They are a temporary kind of placeholder that allows us to understand which way an arbitrary object is rotating. We have to have a direction of rotation, and we choose that direction to be perpendicular to the plane that it rotates in. Okay, that also means that we always have to choose an axis, but I'll get to that later. So by the right-hand rule, the reason why I brought that up now is that positive alpha means that an object in the XY plane is speeding up, the change of its angle is speeding up positively. And negative alpha means that it's slowing down, means that the change of angle is actually negative, okay? That is right-hand rule. If you take your hand and the top one, your thumb points at your chest, and you see that your hand curls counterclockwise, coming out of the page is positive rotation. Alpha is positive, omega is positive. Going into the page, your hand rotates clockwise. That is negative alpha. So just keep that in mind. We've already done this back in like chapter 6 or something, a little bit, but now we need to do it for real. So when something rotates, if we can assume that it's got a constant alpha, exactly what we did before, where remember we had A was dv dt, and we solved this for dv as a dt and assumed that A was positive when we got constant acceleration. We can do the same thing for alpha and for omega. And you can see right away that you already know these equations. If you replace these with x or y, and this with b, and this with a, we know those. Those were the projectile motion constant acceleration equations. They apply here. They tell you exactly what you'll get. Really, really important that you know those. I assume that you already know these. These relationships are, we've been doing them every week. We've used them for something or other. So I'm assuming you know these. The really nice thing is these are the only equations. You don't have an x component to the angular velocity. You just have the angular velocity, whatever that happens to be. It's not to say it's easy, just that eventually we're going to get there. Last thing before we actually start doing some nuts and bolts stuff. So now we know what alpha is, and we know that alpha is acceleration. And we already said that F equals ma is actually not quite true. What it's actually saying is, if I take all the external forces acting on a system and I add them together, that's equal to all the masses times the net acceleration, okay? So we need something for rotation. And for now, so that we have a roadmap of where we want to go, I'm going to tell you that when I have, say, a disk rotating about z, what I do is I sum all these things called torques. We don't know what they are yet. We'll get there. And the sum of those torques is actually equal to I, which is going to take the place of my mass, times alpha, which is my angular acceleration. And that will tell me what the angular acceleration is. And then I can go back here and I can use these to find out things. If it starts from rest, omega, and this is omega initial. Omega initial is 0. Theta initial can always be 0. Wherever you want to start measuring the angle from, you can essentially just say, yeah, it's 0, except for in some weird case. So the rest of our job is going to be to find these two things. The rotational analog to force, which is something called torque, and the rotational analog to mass, which is something called moment of inertia. And we're going to use those so that we'll know that alpha is the sum of all the torques divided by I, just like A is the sum of all the forces divided by M. Our job is really to find alpha, find how fast the angular acceleration of this object is. Next chapter, we're going to talk about what happens when it's 0. But for now, that's our roadmap. Our job for the rest of today is to figure out what I is and what torque is so that we can understand what alpha is and use it in constant angular acceleration equations. Okay, so is there any questions at this point now that all that preliminary stuff is out of the way? We're going to get into some real annoying math. And it's all on here for you, but the math gets tedious. The other problem that students have with rotation is a lot of the math gets very, very tedious. There's a lot of algebra to do. And it gets long and it gets boring. It's just endless, it seems like sometimes. So you've got to pull through and get really good at making sure you know where all your terms are. But we'll talk about that. Okay, first things first. You cannot talk about an acceleration or a rotation without specifying an axis. And so what I want you to do is imagine, I have my calculator. I hope you guys can all see that. But if I wanted to talk about rotating this calculator, I can't just say, yeah, I spun the calculator. That's imprecise, because there's actually three ways I can spin this. I can spin it this way. I could spin it towards the screen, or I can spin it this way. Those are called body axes. I think it's easiest to see with this cube I've drawn here. If I take a cube, I can spin it so it goes around this face, right? The whole cube rotates, spins around this z-axis, or I could spin it around this face, or I could spin it around this face. I could spin it any three ways, any of those three ways to rotate. You're not going to learn it in this class, but if you go on in engineering and physics, you'll learn how to combine rotations so that you can see that any rotation is actually a sum of the rotations along each body axis. And one of those rotations may be zero, and it's only rotating around one body axis. But any complex rotation is really just a rotation around the body axes. We're not going to be complex. We're going to assume that it's rotating around one body axis. But you need to understand what we mean by choosing an axis, because we're going to have to measure the distance to different masses and things from it. Imagine a wheel, the wheel on your car. Your car is rolling down the street, and this wheel's or a car in front of you is rolling down the street. You see that wheel's turning counterclockwise, which is actually negative. How I would know this is see that. I'm sorry, that's actually positive. So the positive z-axis is your thumb, and it points into the screen. And your hand is rotating in the same direction as omega here, this omega. So the thing's rotating positively about a body axis that goes through it. If you were to look kind of from the side, what you'd see is this is z up, and this whole thing is spinning around with some omega. Super important. Omega, same for every mass in that wheel. Okay. They all have the same angular velocity because we're assuming it's a solid, uniform body. That means the masses can't move independently of each other. They all rotate at the same speed. They can all have different velocities. Well, not different, but at least depending on how far out from the axis of rotation they are, they'll have different velocities. That's why we have to pick the axis of rotation. We know that v is equal to r omega. So maybe we know that this thing rotates 4 pi radians in a second. That would be our omega, 4 pi rad per second. If we wanted to know v at, and let's say r is 1 meter, if we wanted to know v, the speed of the masses at half the radius, if r is 1 meter, then at half the radius, we would have 1/2. 1/2 times omega is 1/2 times 4 pi, which is 2 pi meters per second. That's how fast they go. The further out they get, the faster they go. But we have to have an axis chosen so that we can figure out how far away from that axis any mass is. Now, for a disc or a coin, you could also imagine that instead of it rotating around, flat, you could actually have it rolling like around, just like I had this thing. Instead of going spinning like this, I could have it actually rolling. And I could have it rolling in either direction. So technically a disc has 3 body axes. Okay. And omega is the same. And alpha is the same for every particle on it. Now, since we know where the axis is located, we could actually plot from a central point how far every mass is. This is R1, this is R2, maybe this is R3, right? And for each little mass, if we wanted to, we could add up m times r, mi times ri. That just means m1, r1 plus m2, r2. And once we do this sum, that is the moment of inertia of the object. The reason why that's the moment of inertia, that's our new term, that's our m in our torque equation, okay? The reason why we have to add the distance squared is mass, remember in F equals ma, is how resistant it is for a system to change its energy. Well, the energy depends on velocity squared. You already know that. Kinetic energy is mv squared. So the moment of inertia depends on the velocity, which depends on r, which is squared. You can prove this in math. I think you probably have maybe proved this, if not in count 3, maybe in count 2. But the moment of inertia, how hard it is to get an object to rotate, depends on the mass and how far away they are from, I forgot this word, how far away they are from the axis. Okay, so imagine we have a point mass. And what I mean by that is, imagine you have an XY axis, and somewhere out here you have a mass, little mass, and let's say it's at a distance r is equal to 0.5 meters. It has a mass of 2 kilograms, and it's being subjected to some kind of force that's making it rotate around this axis. And this axis right here is z positive. This is y. Okay. The moment of inertia, how hard it is to make that point mass rotate, is just mr squared. We would sum these up, but we only have one mass and it's at one radius. So this thing would have a moment of inertia of mr squared, which is 2 times 0.5 times 0.5, which is 1/2, so 1/4. So this is 1/2 kilograms meters squared. Moment of inertia doesn't have units. It's kilograms meters squared. But that is a measure of how hard it is to make something turn, how much force we have to apply to, well, it tells us how much acceleration it gets from a given force, let's say that, given torque, okay? Single masses are fine. We could have 30, 40, 50, a million single masses and just add them all up rotating around. We can actually treat any solid object as a whole bunch of little point masses, all at their given radius. And in fact, that's what we do. When we do that for an infinite number of terms, we get an integral. If you've forgotten that you were told that in calculus, an integral is the sum of a very large number of operations. And so in this case, if we want to know for a solid object, I is equal to a mass integral, which is not particularly helpful. I mean, how many times have you done an integral of mass of a solid? We're going to change it around. I'm going to show you how to do that next. But the good thing, before anyone panics and looks at all this calculus and goes, oh my God, I don't want to do integrals anymore. I'm doing them in Calc 3 and they're too hard. Before you think that, we're not going to actually do calculus of any objects. Like most things in this class, we're going to choose objects that are symmetric, and those objects are easy to calculate the moment of inertia. And in fact, they're given to you. And so I'll show you where to find that in your book. You can find it online, but I'll talk about those as we go. However, I want you to see how it's done because it's important. Imagine we have a thin rod. And what we're going to do is we're going to take this thin rod, maybe it's my pen, and I'm going to swing my pen around in a circle, okay, about one end. So I need to figure out what the moment of inertia of this rod swinging about this end is. This rod has a mass m and a length L, so I choose my axis to be 0, and I choose the end to be L. This is R. if you want. This whole rod is M, and I'm going to try to swing it around a positive z-axis. That's not super important, but that's what I'm doing. So I have this cool integral, r squared dm, and you might be going, okay, what do I do with that? We're talking about uniform, meaning the density is the same throughout them, thin rods. And if the density is the same, then density is equal to mass over volume, but we're in one dimension. And in one dimension, that means mass over length, or R. If it's uniform, then dm over dr is the same as m over L. That has to be true, right? Doesn't matter how small I take it, it's got the same density everywhere. So when I put P, or rho, over rho in here, this is one, I can totally do that. So I just shove that in. One of them I let equal m over L, and then I still have 1 over rho. And then I have m over L, and this rho is dm over dl. I just flipped it. Or dr, I should say, actually. It's not dl. You'll find a lot of books will choose little l or whatever they want there. I can see that this cancels. I can pull the constant stuff out front. My limits are 0 to L, so I go from 0 to L. R squared, the integral of x squared dx is x to the third over 3, right? Power goes up 1, you divide by the new power. And then I'm going from L to 0. So L to the third over 3 minus 0 to the third over 3. And I get this. Cancel 1L, and I get that this is the moment of inertia of a rod about one end. So if I take something and I were to swing it about one end, try to rotate it around one end, this is the moment of inertia that would resist that term. Now, a much more important thing to know is the moment of inertia about the center mass. So if I do this whole thing that I just did again, except now I'm going to set that this is the origin. So this end is at -3/2, and this ends at 3/2. And if you've ever played with a baton or drumsticks, we're rotating it through the center, trying to rotate it through the center. The only thing that changes from our last integral is our limits. They go from -L to the half to L to the half. And when I do that, I notice that I get a new constant, okay? Furthermore, if I swing it about one end, I just got ml squared to the third. But if I go through the center, I get ml squared to the 12th, which is a quarter of the inertia of trying to swing it around one end. Why? As it says here, why? Well, the reason why is the closer mass is to the axis of rotation, the easier it is to get it rotating. That should be obvious to you. If you try to push on a really long rod on the end, it's hard to get something moving. You can actually get things to spin faster, closer to the center of rotation. And most of the mass in the center one is near the axis of rotation, whereas a lot of the mass is far away from the axis of rotation when you spin it around one end. Therefore, it has more inertia when you're trying to rotate it about one end. So as I said, what you normally end up doing is looking up these values. If you don't have access to your book, you can look them up on the internet anywhere. But when we go to our book, I want to show you the actual page. It's in almost every physics textbook. It better be in every physics textbook. calculating the rotational inertia is what this is called, or moment of inertia. And when we do this, eventually, maybe, this chart right here, I advise you maybe write down somewhere, put on a Post-it note, whatever, especially if you're an engineer. Essentially, all you're ever going to do is if you need I, you're not going to write an integral. You're going to look at this table and go, oh, I have a thin hoop. I is mr squared. Or, oh, I have a hollow sphere, thin hollow shell sphere. Moment of inertia is 2/3 mr squared. Oh, I have a door, blah, blah, blah. In general, you just, well, in practice, what you do is you look up the moment of inertia of an object. One kind of interesting thing that might help you to understand what's happening here is imagine I have that wheel, and this is the one that I do want you to commit. The two I want you to commit to memory are points are always mr squared, and wheel or disk, I is mr squared over 2. If you guys take the MCAT or GRE or something, and you ever need the moment of inertia and you don't know it off the top of your head, really good guess, mr squared over 2. If you come back and look, all of these are ml squared or mr squared with some constant in front. In general, you're going to be pretty close choosing a half. So if you ever can't remember, just go with mr squared over 2. But that is for a disk rotating through its center, okay? That is I if this thing is rotating about its center. Now, a cylinder, imagine a cylinder. And with this cylinder, if we're rotating through the body, so it's rotating through the body, what is I? I is mr squared over 2. Why would a cylinder be the same as a wheel? What's the same between a wheel, and by wheel I mean a thin disk, and a cylinder had the same moment of inertia? The moment of inertia depends on the mass distribution about the axis of rotation. And that's really important. So even an infinitely long, infinitely massive cylinder would have the same form. Its moment of inertia would be really big because its mass would be infinite, but it has the same form because what matters is the distribution of the mass about the axis of rotation. Now, as I said, in practice, you write down I is mr squared over 2 for a disk, and you don't think too much about it. But there are times where you do need to figure it out. And usually what happens is maybe you have, instead of just a rod, right? Maybe you have a rod with a disk on the end, okay? And what are you supposed to do at that point? Or maybe you have a rod that's swinging around its center of mass. So it's rotating while it's rotating. What would you do? Turns out what you do is something called the parallel axis theorem. I already said that I had a rod about its center rotating. So it's rotating about its center. This is Z, this is omega. This thing's spinning around. I can actually move the axis of rotation to any parallel point as long as I don't change the direction of the vector. So what I'm going to do is I'm going to move it instead to one end. So now I'm rotating about one end, and I'm going to use that to figure out what the moment of inertia about one end is. This is what is called center of mass. I'm going to move it to one end. I center of mass we already found was ml squared over 12. The parallel axis theorem says that the center of mass plus the mass times the distance you move the axis away from the original axis gives you the new parallel axis moment of inertia. When we move from here to there, or from here to there, it doesn't matter. We move from here to there, then d in this equation is the distance from the axis that we move to the new axis. We moved a distance of L to the half the length. If I plug that in, I get the center of mass is ml squared over 12. Okay. I add m times the distance I moved the axis, in this case L over 2 squared, or L squared over 4. If I multiply this by 3 over 3, I get 3/12. If I add those together, sorry, Juwan, I know that says private, but for the quiz, in collision 1, after mass 1 is at rest. Before the collision, mass 1 is moving, mass 2 is at rest. They hit, mass 1 stops, mass 2 keeps moving. Anyway, so once we have this and we add ml squared over 12 plus ml squared over 4, if I multiply by 3 over 3 to get the denominators the same, I get 3/12 plus 1/12 is 4/12, which is ml squared over 3, which is exactly what we found for the moment of inertia of a rod about one end that we found through calculus. We could have found it from the parallel axis theorem. It's really powerful and really useful because you can find a moment of inertia for an object that you know the moment of inertia about its center of mass, simply by knowing how far away from that axis you move. A little bit harder concept is that the total moment of inertia of any system is equal to the moment of inertia of all the parts about that axis. How I'm going to show you that is we already just saw that for a rod about one end, so it's rotating about Z coming out of the page, okay, for a rod about one end that we should get ml squared over 3. Imagine instead this rod were made up of 2 separate rods. We know that this rod, okay, about one end is going to be ml squared over 3. But this rod has half of the mass and L is half. So I have to put in m to the half and L to the half squared over a third. For this guy though, I know its center of mass. I know the center of mass, and I know that I'm going to move its axis half of the length plus another quarter of the length. That's 3/4 L. So I know that this I center of mass is m to the half times L to the half squared over 12. And then this is m to the half times d squared. And when I do all this algebra, all this tedious algebra, I see that it comes out as ml squared over 3 again, as it should. But what I've done here is I took the moment of inertia of the first one as a rod about one end. And I used that the mass was half the mass of the total rod, and that L, the total length, was L to the half. Okay. For this one, I used the parallel axis theorem. And when I did that, I plug in the center of mass, remembering again that m is m to the half and L is L to the half. And then, knowing that about the center, it was ml squared over 12, plugging all that stuff in. It's not too hard. I would recommend going through it once or twice. We're going to use it probably on exams. You can use it for, imagine this and see if you could think your way through this really fast without us actually doing it. Imagine I had a sphere and I had a sphere and I had a rod that I said went from the center of the sphere and I want to rotate this thing. And the rod has a mass m and an L, or a length L. These spheres have a mass m and a radius r. And then I need to figure out the total moment of inertia if I try to rotate this thing about its center of axis. What I would have to do is, for the spheres, I would have to use I parallel axis is the center of mass of a sphere plus md squared. For a solid sphere, that's mr squared times 2 times 2/5. And d would be, from here to here, would be L to the half plus mL to the half squared for each of them. And then I would still have mL squared over 12 for the rod. So plus 2/5 mr squared plus mL to the half squared. And that would be the total moment of inertia of two spheres connected by a rod being rotated about its center. You can see that this gets a little complicated sometimes, but it's not as complicated as writing up the calculus. Trying to integrate all that mass is a huge pain, and we're not going to do that. We can do this because all these objects have symmetry, and they're all uniform by our choice. And again, on Thursday, we're going to go through some problems with these, where we're actually going to maybe plug in some numbers and use them where we need to use them. We might not do this type of particular thing, but I guarantee you at some point you're going to have to figure out the moment of inertia of two objects. And hopefully it makes sense to you. So as I said, though, for the most part, these are the moment of inertia about the center of mass, usually, of a bunch of common objects. And when you look here, you can see that this is 2/5, this is 2/5, I mean, this is 2/3. This is a hoop through its center as mr squared, but through its y-axis or z-axis, as it spins, it's 1/2 mr squared. So it's the same as a disk. So don't write these down in your notes. I mean, maybe put them on a Post-it and stick it next to your computer somewhere, but just know where to find it if you need them. The ones I want you to know are point mass, mr squared, disk, mr squared over 2, and the spheres. Spheres we end up using, why? Well, because you know we're going to have like a hollow sphere rolling down an inclined plane, right? And need to figure out the energy at the bottom. So we're going to need those things. That's all well and good. If you understand what the moment of inertia is, you can look them up on the tables where you need them. Remember that we're trying to solve the sum of the torques is I alpha, and we've found I now. If it's a point mass, I is mr squared. If it's some other shape about its center of mass, it's 2/5 mr squared or whatever. If you have to move that center of mass axis to one end, you use parallel axis theorem. If you have two objects, you can combine their moments of inertia. Okay. So now we got to turn our attention to this. And before I do that, I want to talk about something that you may or may not all have done in your life. I hope you've all done this. Imagine you have a bolt and you have a screw or a wrench, and you're trying to turn this bolt. You already know that this is a human experience, right? You pull up on that wrench with some force and everything turns, right? Everything rotates around an axis through the bolt. So this is your Z, this is your omega or your alpha, but you make it turn. We're going to define for the system, this is our axis, Z. R goes to the point where the force is applied, and then we draw a vector F. more importantly, we're going to draw F and R tail to tail, which we can always do because they're vectors. We can pick them up as long as we don't change their direction. And then we somehow need to come up with something that tells us what happens. Now, we said that I had units of kilograms meters squared. And we know it's being multiplied by alpha, which was rads per second squared. So I alpha is going to be kilograms meters squared over second squared times rads. I want you to look at this though. This is super important if you're still here and paying attention. Please pay attention to this. That right there is kilograms meters per second squared times meters times rad. Rads are not units, but these are. What is this? What is I alpha? It's Newton meters. What are Newton meters? Well, they're energy, but they're not quite energy, but they're energy. They're not quite energy yet, but they will be. Just know that the units are not newtons. I alpha doesn't equal newtons. Torque is not newtons. It's newtons times meters, which tells us that our torque had better have units of Newton meters. So we have two choices. We can dot F or we can cross F. And we can already see that F and R are 90 degrees off. We're going to cross. So what happens is we say the torque is R cross F, not F cross R cross F. Remember that R cross F is equal to negative F cross R. If you cross them wrong, you get the wrong answer. Assuming R lies along X and F lies along Y, if I turn or cross R to F, I can see by the right-hand rule that that is a positive rotation. Or I can write R, F, sine of the angle between R and F. And I know that this is 90 degrees right now as I turn R to F. So sine of 90 is 1, obviously. This is in the z hat. Everything here is positive, and I get a positive torque. If R turns to F counterclockwise, I get a positive torque along the z-axis. That means, just like with F equals ma, right, that the force causes me to speed up, a positive torque causes me to rotate counterclockwise in the positive z direction, okay? If the torque were negative, then it would cause me to rotate clockwise. But torque is R cross F, where for whatever your axis is, if I apply, I don't know, if I apply a force to the outer edge of a disc, so I push up here with some force, I draw R, this is R, the distance from the axis to where the force is being applied, I draw the force, I turn R to F. If it's counterclockwise, I call it positive. If, on the other hand, this were F prime, then I would have R and I would have F prime. Turning R to F prime would give me a negative alpha or a negative torque. You could also write positive omega, negative omega, whatever you want. Cross products though, you turn R to F. You either draw them or you write them. I'm not going to write them again. This is sufficient for what we need. It's RF sine of phi, where phi is the angle between R and F. In general, about half the torques we have are going to be at 90 degrees. So I alpha is going to be RF. We're going to have one torque and we're going to get RF. As an example, let me show you this. Imagine I have a pulley that can rotate through. And I'm going to come back to this full example later, but this is my body axis of my thing. This mass starts to fall. I know that right here, I have a tension pulling down and I have a tension pulling up on this mass. But for the wheel, what I have is I have a tension force of tension at the radius of the disc. This, if I use the cross product, I can see that this is a negative alpha. This causes my pulley to spin clockwise. We're going to come back to that again and again, but just so you know, that's what's happening. So let's look at a few quick examples of different things that could happen. Back to my wrench turning. If I push down on my wrench, what happens? R and F, R is that way, F is that way. If I turn R to F, I'm turning clockwise, negative direction. My torque is negative I alpha. Okay. If I pull up, my R is this way, my F is this way. I turn R to F, that's a positive counterclockwise rotation. My torque is positive I alpha, or I alpha in the positive Z direction. But the final one, and this should make hopefully a lot of sense to you. My final one is, what about if I pull on the wrench? So I pull on the wrench. Well, I said that torque is RF sine of the angle between them. If R and F are in the same direction or opposite directions, the angle between them is 0 or 180 degrees. It's 180 degrees if R is this way and F is this way. It's 0 if they're this way. Sine of 0 is 0. But that should make sense to you. If you pull on a wrench, you're not making it turn. You're just pulling on it. You're making it translate or move laterally. So this torque is 0. The last thing that we could have, the last case, is what if you didn't pull straight up? What if you did pull at some angle 30 degrees? Well, you have F at 30 degrees, you have R, so you need the component of F that is parallel, or I mean perpendicular to R. That is F sine of 30, but we already know that. This torque is RF sine of 30. We already know. So if it's at an angle, you just get the component that's perpendicular to your R vector and solve for the torque. That's all there is to it. Torque isn't that bad, except for when you get 20 of them, 30 of them. That's not usually the case. But yeah, torque is simply finding R and finding the component of F perpendicular to R if there is one. If there's no perpendicular component, meaning no 90-degree component to R of the force, then it's not rotating. It can't rotate. There's no way for it to rotate. Nothing's making it rotate. In order to rotate, it has to be a force applied at some distance from the axis to the mass to make it turn. Again, we can do a pulley example in a little bit more detail, and I'll do it on a new slide. Imagine that I have some pulley that's mounted on a bracket, and it's got a rope around it, and I start pulling with some tension. And so this thing starts to spin clockwise, which we've already said is negative. So this is negative omega. This is my Z hat direction, and I'm pulling with this tension. That means that at a distance R, which happens to be the radius of this wheel, I have a tension force. What I normally do, and what I'll expect you to do at least on the next test, is whenever you have torque diagrams to draw R and F or R and T, and show the turn from R to T and whether or not it's positive or negative. This is negative alpha, right-hand rule. I'm turning R to T. R cross F. And because I'm going clockwise, it's negative. All right, so I know that I have I alpha is equal to R T. But this is going to be negative, okay, from this. So what I really do is I write T is I alpha and T is negative RT is I alpha. Alpha is negative RT over I. Now, what's funny about this is alpha for a disk, I is mr squared over 2. So this becomes negative R over mr squared over 2 times T, which is negative 2T over mr. And that gives us the angular acceleration. If we started from rest, we could find the angular velocity when t is equal to 10 seconds. Well, time is equal to 10 seconds. We could go on and do all sorts of fun problems with this. But this is the key concept. We have a force being applied at some distance from the axis of rotation, and that causes a rotation. And in this case, it's negative because it's clockwise direction. When I turn R to T, I'm going clockwise. You can follow this example if you want. I solved it here. If M was 2 kilograms and R was 1, mr squared over 2 would be 2 times 1 squared over 2, which is 1 kilogram meter squared. And the force, if it was 10 meters, means that's, or 10 newtons, that's the tension. So I get that alpha is negative RF sine of 90. R and F are 90 degrees off over I. R is 1 meter, so negative 1 times 10 newtons over 1 times sine of 90 is negative 10 rads per second squared. And like I said, you could then jump back to the constant angular acceleration and use those to find whatever information I asked for, assuming maybe the pulley starts at rest, or the, maybe it's slowing down, or whatever it's doing. Note 2, negative alpha can mean either the rotation slowing down, omega's decreasing, or it could mean it's starting from rest and it's turning in the negative direction, okay? Meaning it's turning opposite what we call the positive direction, which we see here. If it were turning clockwise, if it were going around like this, it would be positive. So our negative alpha tells us that it's rotating the other way. All right. Now, finally, out of all that, when something rotates, we already said that a block has mv squared over 2. But now for the rotating object, all of these have little v's, and they're all different. Well, it turns out that if we know the moment of inertia and we know omega, which is omega is the same for all of them, that we can write I omega squared over 2 as the kinetic energy. Is it kinetic energy? Meters, kilograms, meters squared. Omega is rad per sec squared. This ends up being kilogram meters over second squared times meters. So it's certainly energy. However, here's the tricky thing. If something rotates, it can also translate. So you could think of like a potter's wheel that's spinning, and you would say, oh, well, that's I omega squared over 2. It's just a spinning wheel. But you could also think of a car wheel rolling along the ground. The whole wheel is translating as well. So because it's translating, because it's moving in the x direction, it has mv squared over 2, but it's also rotating. And because it's rotating, it has energy I omega squared over 2. And what this means for us is that when we write our energy equation, mgh plus mv squared over 2 plus kx squared over 2, we have to now include I omega squared over 2 for anything that's rotating, which makes it somewhat easy. Maybe not super easy, but It's a small change. Imagine that you have a hollow sphere and it's on like a little pedestal that's massless, and you spin it. Maybe it's a globe, and you walk over and you spin that thing. If it starts spinning, you know that the points on the outside, okay, VT is R omega. So V is really R omega, and omega is constant and R is constant for this spinning globe, okay? Therefore, we can take I omega squared over 2. We can write I as 3/5 m R squared times omega squared over 2. I always forget those 2's. This is V squared, which means this thing has 3/10 mv squared. It doesn't have the same kinetic energy it would have if it was just sliding without rotating at all. And it has less kinetic energy than it would have if it was rolling down a hill. But just by virtue of it spinning, it has a kinetic energy. Now, if it were a solid sphere, this might be a 2. But if it were a solid, total solid sphere, you would have a 2/3 out front, so you would get essentially a third mv squared for its rotational kinetic energy. So let's look at that again. A block sliding has kinetic energy mv squared. A wheel with the exact same mass as this block and with the same velocity, okay, has extra. What you do is you write for the block sliding, you write, oh, the kinetic energy is mv squared over 2. But for the wheel, as it rotates, you write kinetic energy is mv squared over 2 plus I omega squared over 2, where I for a disk is mr squared over 2. So I omega squared over 2 is m r squared omega squared over 4. This, though, is v squared. So this term is mv squared over 4. This is the normal kinetic energy. Add those together and you get 3/4 mv squared. What you should be seeing here, what I'm trying to get through to you with this example, is that the rotational kinetic energy is energy as well. If you were to try to stop this wheel, it would take more energy to stop a rotating wheel than it would take to stop a sliding mass. Rotation sucks up energy. And actually, when you put energy into a system that rotates, you actually end up losing energy to that rotation or storing energy in that rotation, which is pretty neat. But technically, all it means for us is that where you might have previously wrote mv squared, if it's rotating, you better include I omega squared over 2. Second, you can then, using the proper moment of inertia, you can relate omega and v and get everything in terms of mv squared. That's helpful. We're going to see that on Thursday. We may see it at the end of today, actually. Okay. So we talked about, we're going to see it right now. We talked about torque and we talked about rotations, and we've got rotational variables. I want to do a problem in 2 ways and really show you how this works. So we already started this problem, but I'm going to do it again. So this is a pulley. It's going to rotate about the negative z. So I don't have to do negatives. I'm actually going to have it rotate around the positive z. I don't feel like dealing with signs right now. This is positive z. How do I know it's going to rotate? Well, I'm going to attach a mass with a massless, stressless string. Okay, z hat. this thing going to rotate this way when I let this mass fall. So the mass of the pulley, let's say it's 3 kilograms. And the mass of the block, let's say it's 4 kilograms. I don't really care. Let's say the radius of the pulley is 1 meter. And we're going to start it from rest. But we need to determine, if we let it fall from rest, what is the acceleration of the block? What is the velocity of the block? What is omega? Doing this with Newton's equations is a bit of a pain, because what we have to do is we have to draw 2 free body diagrams. And one's the normal one that you all know. T, this is M, this is mg, and this is obviously the block. And A, I'm going to assume is straight down. So I get the usual MA is mg minus T. However, for the pulley, I have to do a torque diagram. And what that means is I draw at some radius the tension. I actually draw it twice because I always want to turn R to T. This is a right-hand rule. When I try to push R to T, I see that my thumb points towards me. That is a counterclockwise positive rotation. This is all you need for a torque diagram. You need to show the radius, the force, and the acceleration, positive or minus. So from this, though, I know that I have I alpha is the sum of the torques. I only have one torque, and that torque is RT, and it's positive. I can solve this for T. I alpha over R. But here's the thing. When I plug in for T, I get MA is mg, and these I'm going to say are the block, minus I alpha R. So now I have alpha, I have R, I have A. I know these M's. I can find that I for a pulley is going to be mass of the pulley times R squared over 2, just like a wheel. So I know what I is, but I have alpha and I have A, and that's a problem. If we go back and we look, we said that S was R theta, V was R omega, and A was R alpha. Therefore, alpha is A divided by R. I know at this point, this A is equal to R alpha at that point. So I can substitute that in. Mg minus I alpha is A over R. So A over R squared. Okay. So what I've got right now is I have MA is equal to mg minus I A over R squared. But I is mr squared over 2, but this is the pulley. Okay. So this, I'm just going to actually put in as a number. That was 3 and 1. So this is 3 times 1 squared over 2. So I is 3/2. Do I want to do that? No, I don't. I'm going to call it mass of pulley. So MA is equal to mg minus mass of pulley times R squared over 2 times A over R squared. That goes away. I'm going to move this to the other side. And what I get is I get M of the block, A, plus M of the pulley, A, over 2 is equal to mg. Solving this for A, I get mg over M plus mass of the pulley to the half. This is the acceleration of my block. If it falls from rest and I let it go, so V initial is 0 and I let it go a distance of 3 meters, let's say, and I want to know what V final is. Now, let's actually do just time. Let's say I let it fall for 2 seconds, and I want to know what V final is. V final is V initial plus AT. This is 0. I multiply this by 2 seconds. what did I say that was? 4. 4 times, I'll just use 10. 4 plus 3/2, which is 5.5. 40 divided by 5.5 is 7.3. So V final is equal to 7.3 times 2, which is 14.6 meters per second. I want that for a reason. Okay, so what I had to do here was I had to get a free body diagram of this block, which I did here, and get this equation, Newton's equation. For the pulley, I had to draw a torque diagram. It had a torque from the tension pulling it down at a distance r, and that's what I drew here. I make that a torque equation by writing I alpha. Just like when we write MA for the forces, we write I alpha and we list all the torques that apply to that pulley. There was only one torque on this pulley. There's only one force acting on this pulley, and that's the tension from the mass. So I write that down, RT, and there I solved for T. I put it back in here, and then I had to substitute for alpha in terms of A, which I substituted A over R, and therefore I got everything in terms of the acceleration, the translational acceleration of the mass of the block down. Now, here's the fun thing though. I can do this a totally different way. This is why energy is so useful, okay? Before this thing starts to go, before it starts to fall, I'm going to assume that y is 0 for this guy and y is 0 for him. So I write the energy initially. The initial energy, I have to write mv squared over 2 plus mgh for the block, plus mv squared over 2 for the pulley, plus I omega squared over 2 for the pulley, plus mgh for the pulley. But it has no change in potential energy, so I'm going to get rid of this. And it's not translating. Yeah, they're translating, but the whole thing isn't moving anywhere. So the initial energy is mv squared over 2 plus mgh plus I of the pulley omega squared over 2. The final energy, once this thing's fallen, oh, and this is 0, okay? And I'm saying this is 0, and it's not moving. So this whole thing is 0. The final, once this thing starts falling with some velocity, okay, it's going to be at negative h, right? We need to know what h is, but we'll get there in a minute. And this thing is now rotating with omega. So the final energy is m of the block v squared over 2 plus mgh of the block, final, plus I of the pulley omega squared over 2. So we'll write that a little bit cleaner. So initially, energy initial, nothing moving. We can just write down that that is 0. Then energy final, what happens is the block is now moving, the pulley is now rotating, and the block has gained some change in potential energy. All right, one last thing that we can do here is we can plug in. So E initial is equal to E final as long as there's no outside forces. mv squared over 2 plus, this was the mass of the pulley times r squared over 2 times omega squared over 2 plus mgh final. H final, we're going to say is -3 meters or something. I don't really care. Let's say it's -3 meters. we're finding the velocity after it's fallen 3 meters. So now what I have is this becomes v squared. And what I get is I get 0 is m to the half times v squared plus mp over 4 times v squared plus mg times -3. So I can move that over if I want to. But I can solve this for v. And so what I get is I get 0, well, let me actually just move over that mgh. So mg times -3 becomes +3 is equal to m to the half plus mp to the 4th times v squared, or v is equal to 3 mg over m to the half plus mp over 4 to the 1/2. So I take the square root of all that stuff. And that I can easily solve. Now, I don't know, I'm going to show you how to do this, but essentially what I really wanted to show you was when we have something that rotates, we still do energy the way we did it in chapter 8. We just add the term for the kinetic energy of rotation. And in fact, it makes it super easy to just quickly write down what's happening. The only hard part of this, I would say, that I wasn't very clear on is initially V is 0, this is M, this is MP. Omega is 0. And we need to figure out what is H. I chose H to be 0 so that I could write down the initial energy was mv squared over 2 plus mgh plus I omega squared over 2. This has no potential energy of gravity. It does, but it's not going to change, right? And it has no translational velocity as a whole. That pulley is not going to fall. So I know this is 0. I've chosen this to be 0. I know this is 0. After it falls, right, now H is -3. And now V is unknown, but definitely a number. And now omega is definitely a number. And so now the energy is mgh plus mv squared over 2 plus I omega squared over 2. And then I can use V is R omega at this point. Every point on the edge of that pulley has to be traveling at the same speed as the mass that's falling. It has to be. So therefore, V here is equal to R omega. And using that, I can turn omega into V, or I could turn V into omega. It's really up to you. Set the energies equal, and you've solved for velocity. At that point, if you want to get the acceleration, you could use omega final squared minus omega initial squared is equal to 2 alpha, you know, assuming that you knew the change in the angle or whatever. One thing that you sometimes run into, and we'll talk about this more later, is we could actually attach a mass to the inner and to the outer, and these guys will have different V's. Because as this one falls, as this block 2 falls, it unspools more than this, right? So as this thing turns so that 2 can fall, 1's going to go up much faster than 2. And we'll do a problem like that next time, where we'll talk about how to deal with when you have different radii. But for the most part, if I had 2 masses connected here, we would know that V and omega would have to be the same because they're connected at the same radius from the center of rotation of the pole. Okay. There's a lot to take away from this chapter. And then we haven't even started trying to do problems with this stuff yet, which is why I wanted to divide it up a little bit. But the main takeaways here are know your rotational variables, theta, omega, alpha. Know those constant angular acceleration equations. Make sure you understand torque and how torque works as RF sine V, okay? And that torque causes rotation. And then, and some of the torques actually, and then know the kinetic energy of rotation for a object. Know that you need to find I, and if you were given omega, you could quite easily find omega, but more importantly, you usually use V R omega or A R alpha to find, to relate things, whether you're doing it with Newton's equations or energy. So there's a lot to know in this, but essentially, once you start doing these, you're going to find they're not too bad. And once you do a few torques, I don't think torques are too bad. Just remember that you always draw R from the axis of rotation, AOR, to the point where the force is being applied, and then reset them tail to tail and turn R to F, using right-hand rule if you need to. But that's it for today. It's a lot. I went through it in an hour and 44 minutes without a break. So I'm sure you guys are probably as glazed over as I am. We're going to go through questions on these. I'm going to try to get some simple questions that we can talk through these next time. But I want you to have enough time to kind of maybe synthesize it a little bit before now or before Thursday. Lab Thursday won't be bad. There's no lab report due Thursday. So if anyone has any questions for me, let me know. Otherwise, you can go and read through the chapter and maybe make some notes, do what you need to do. Alrighty. Thanks, everybody.
Thank you so much, Professor.
Thank you, guys.
Have a wonderful day.
You too.